Hello and welcome back to Engineers Olympiad, where learning meets success. We're on to second chapter of Surveying, that's Theory of Errors. We have completed 4 video lectures of the same chapter. Now this is the video lecture number 5, and we'll be studying about propagation of standard errors. We know that our standard error is same as standard deviation, which is our indicator of determining the relative precision and is an indicator of how reliable our set of measurements are in a given set of measurement. All right. Now we'll study about propagation of standard errors because in surveying, much data is obtained indirectly by computation of observed quantities. For example, if we'll be taking, let me take an example of coordinates of points, all right? And how do we get them? By finding the lengths and bearings of the lines. All right? So in surveying, much data is obtained indirectly by computation of observed quantities, and our coordinates of certain points, let's suppose, are obtained from the lengths and bearings, all right, of lines. And because each measurement contains some error, the computed quantity will also contain some error. As already discussed in the previous lectures, that it is impossible to determine the true value of a quantity, and this true value is rather a hypothetical quantity. Why? Because it's impossible to determine true value. True value is arithmetic mean of infinite number of measurements of that particular quantity. If we'll take infinite measurements of a particular quantity, let's suppose anything, let's suppose width of this whiteboard. To determine its true value, we have to take infinite number of measurements, and when we'll calculate their arithmetic mean, it will be its true value. But it's not possible to take the infinite reading. So this true value is a hypothetical quantity and we cannot measure it, all right? Because there is no end to such refinements of how precisely I can measure or how accurately I can measure the width of this whiteboard. So this true value is a hypothetical quantity which cannot be measured, and it's usually considered that it is arithmetic mean of infinite number of observations of that particular quantity whose value we have to take. And I had already discussed in the previous video lectures that the closest to true value is most probable value, and this most probable value in a given set of measurements is arithmetic mean. And please do not confuse this with the most probable error, which is 0.6745 times the standard deviation. That is something else, and this is something else. Let me illustrate it once again, that it's impossible to determine the true value of the quantity because this true value is a hypothetical quantity item, because we cannot determine it. To determine a true value of any quantity, we have to take infinite number of measurements, and it is impossible to determine true value. We cannot take infinite number of measurements and then calculate their arithmetic mean, which will be equal to true value. So in surveying or in most of the general operations, what we do, we take this thing, most probable value, which is equal to arithmetic mean in a given set of measurements, and we take that this value is most closest to the true value, and the chances of this most probable value of being true value is quite high. And please do not confuse yourself with the most probable error, which is 0.6745 times the sigma standard deviation, and this is something else. All right, this is error and this is value. And in a given set of measurements, we take arithmetic mean of those measurements as most probable value. All right, let's get back to our topic, propagation of standard error. So already discussed that in survey, much data is obtained indirectly. For example, we have to calculate the coordinates of the points, we'll calculate the lengths and the bearings of the lines, and we'll compute the results, and then our computed quantity will also have error, because if my measurement has error, then if I have to do some mathematical operations of addition, subtraction, multiplication, etc., my errors will propagate. My standard errors, which are also known as standard deviation, they will also propagate, and my computed results will also have some sort of an error. All right, because as already discussed, it is impossible to take a reading which is error free. Our errors always creep in our measurements, and the true value is that value which is free from every error. All right, so we have to see how we can calculate or how we can assess that how these standard errors propagate in our computed results when we do mathematical operations of addition, subtraction, multiplication, etc. All right, so let's study how we do that. Let me rub it first. All right. All right. So the combined effect of errors of the observed quantities on the computed or derived quantity is found by differentiating with respect to each of the observed quantities and then summing them up to obtain the total effect. We then sum them up to obtain their total effect. Whose total effect? Total effect of errors and how they propagate in our computations. All right. So we compute the combined effect of the errors of the observed quantities by differentiating with respect to the observed quantities and then summing them up to find the total effect. Now let me illustrate it. How do we do this? All right. Let us consider a derived quantity A, which is computed from three observed quantities x, y, and z. All right, thus I may write it that A is a function of x, y, and z. All right, I have taken a derived quantity A. This is a derived quantity. All right, A is a derived quantity which is computed from three observed quantities. Let me write it down. This is a derived quantity and these are the observed quantities. All right, so A is a derived quantity which is computed from three observed quantities x, y, and z. Then I may write that A is a function of x, y, and z. All right, now the total error in A is given by delta of A. All right, and we'll take the partial derivatives tf dou f by dou x delta x plus so on. All right, sorry, it's z. All right, now the standard error in A due to standard errors sigma x, sigma y, and sigma z, etc. is obtained by following relation. Now I have to calculate, this is the total error in A. This is given by the partial derivative equation dou f by dou x delta x, dou f by dou y delta y, and dou f by dou z delta z, plus so on so forth. This is the total error in A. Now I have to compute the standard error in A. This is given by this relation, the square of it. All right. So this relation gives us the standard error in A due to standard errors sigma x, sigma y, and sigma z in the observed quantities of x, y, and z. And this is the general expression. This one. This is the general expression for the standard error, and this can be used as in various cases of addition, multiplications, quotient, etc., which we'll be studying in a bit. All right. So this is the general expression of propagation of standard errors in any equation, and we'll compute all the cases by following or by using this general equation. All right. So we had a derived quantity A, which was obtained by three observed quantities x, y, z. So the A is the function of x, y, and z. Now this was the total error in A, which was given by this relation, and the standard error in A by standard error of this quantity, and this quantity is given by this relation, and this is the general expression for the propagation of standard errors. And as already discussed, that we compute the combined effect of the errors of the observed quantities by differentiating with respect to each of the observed quantities and then summing them up to get the combined effect of the error. All right, now let's take the cases. We are using partial derivatives. All right. Addition or subtraction of quantities. Addition or subtraction of quantities. And how we use the general expression to find the combined effect of the errors that creep in my computed quantities, which are derived from taking various observations that form my observed quantities. All right. So let us consider a quantity A which is given by this expression A plus B, where A and B have the standard errors of sigma A and sigma B respectively. All right, I have taken a quantity A which is a function of A plus B, and where A and B have the standard errors of sigma A and sigma B respectively, and I'll use a general expression, that is, how will I now replace it? It will become standard error in A, square of it, plus all right. So I have taken the general expression and I have replaced it with this function to compute the standard error in, I'll denote this by capital A, all right, in A. All right, let's solve this. Sigma A square is equal to, this will become all right by solving. Now what will my sigma A be equivalent to? Plus minus under root of sigma A square plus sigma B square. All right, let's suppose my sigma A and sigma B are equal. If sigma A, standard error in A, is equal to standard error in B and is equal to, let's suppose, sigma, then how will my expression change? It will become sigma A is plus minus sigma A square root of 2. All right. So in general, I may write that sigma A is plus minus sigma A n raised power 1 by 2. Alright, where n are the observed quantities. Alright, students. So in general, if a computed quantity is equal to the sum of two or more observed quantities, the standard error of the computed quantity is equal to the square root of the sum of the squares of the standard errors of the observed quantities. Alright, let me take the case of subtraction. Likewise, if my function is now a minus b, and sigma a and sigma b are the standard errors in a and b, likewise, my standard error in a is equal to plus minus under root of sigma a square plus sigma b square. Alright, so the case is similar in case of addition or subtraction. And what is that? That if a computed quantity is equal to sum or the subtraction of two or more observed quantities, the standard error of the computed quantity is equal to the square root of the sum of the squares of the standard errors of the observed quantities. Alright, this was case number 1. Now let's take product of quantities. Product of quantities, right? Let us consider a quantity A, F, which is equal to A multiplied by B multiplied by C. This is the expression. We have to use the general expression to find the standard error in A. Now, taking the general expression, I may write it down that sigma A square is equal to alright, by solving alright, this will become alright. I may write it down as, if I'll take this common, alright, sigma C by C, square of it, right? Or I may write that my sigma A is plus minus ABC and the square root of it. Let me write it as sigma A by A square plus sigma B by B square plus sigma C by C square and a square root of it. This will be my standard error in A. Plus minus ABC, sigma A divided by A square of it, sigma B divided by B square of it, sigma C divided by C square root, sum of all, and the square root of the general this. All right, so this is the case of product of quantities. Well, we'll be having such an equation, how we can find the standard error in the computer result. All right, we'll be taking examples later and then we can study it furthermore. All right, next one, quotient of quantities. Let me drop it first. All right, quotient. Let us consider a function AF, which is given as A by B, or A. All right, we have to find the standard error. We will use the general expression, and I may write it down. Sigma A square of it will be equal to square of it. I'm using the general expression, all right, in every case. Square of it, all right, or sigma A square. By computation, this will come equivalent to sigma A by B square of it, and this will be equal to sigma B. This will be divided by B square, and minus will come by derivative, and A square of it. All right, minus A sigma B divided by B square of it. By further solving, my sigma A will be equal to how much? If I'll take A square and B square as common, I may write it down as sigma A divided by A square of it, and plus sigma B divided by B square of it. All right, my expression is A square by B square, sigma A by A square of it, plus sigma B by B square of it. Or I may write that sigma A will be equal to plus minus A by B. All right, sigma A divided by A square of it, plus sigma B divided by B square of it, and by taking the square root. All right, so this becomes the expression for propagation of standard errors when we'll be having case like this, quotient of a quantity. All right, next one. Next case is that of a power of a quantity. All right, let's consider a quantity A, which is given as A raised to power 1 by n. Let's use the general equation and find the standard error. Sigma A square is equal to A raised power 1 by n sigma A square of it. All right, by solving, my sigma A square is equal to how much? 1 by n A raised power 1 by n minus 1, and my sigma A square of it. Further solving, this is equal to how much? 1 by n a raised power 1 by n divided by sigma a by a square of it, or sigma a is equal to plus minus a raised power 1 by n divided by n multiplied by sigma a by a. All right, and raised power 1 by 2. This becomes the general expression. No, it was square, so I need not to put any square root, right? This becomes the general equation when we have to find the propagation of standard errors, when we'll be having expression as power of a quantity. All right, next one, addition of a constant to a quantity. During solving numericals, each and every expression will come handy. Addition of a constant to a quantity. Addition of a constant to a quantity. All right. Let us consider a function AF which is equal to a plus minus some constant k. All right, let's use the general expression sigma a square. It will be equal to all right. By solving, my sigma a square is equal to how much? Sigma a. All right, square of it. So sigma a is equal to sigma a. So if a computed quantity is equal to the sum or difference of an observed quantity and a constant k, the standard error of the computed quantity is the same as that of the observed quantity. All right, this must be noted. I may illustrate it once again, that if a computed quantity is equal to sum or difference of an observed quantity and a constant k, the standard error of the computed quantity is the same as the standard error of the observed quantity. Moving on, next one. Next one is product of a constant. Product of a constant. Let's consider a quantity AF which is equal to how much? K times A. Let me use my general expression. Sigma A square is all right. By solving, my sigma A square is how much? It is K times sigma A square of it, or I may write sigma A is plus minus K times sigma A. All right. So if a computed quantity is equal to an observed quantity multiplied by constant k, the standard error of the computed quantity is equal to the standard error of the observed quantity multiplied by that constant k. Let me tell you once again that if a computed quantity is equal to an observed quantity multiplied by some constant k, then the standard error of the computed quantity is equal to the standard error of the observed quantity multiplied by the same constant k. Moving on, next case. I think my every case is complete. We have done addition, subtraction, multiplication, quotient, power, root. We have also done addition of a constant to a quantity. Then we have done product of a constant as well. All right, with this we have completed this propagation of standard errors. And in the same manner, if we'll be using probable errors instead of standard errors, my general expression will be right. I'm sorry, I have to use the, let me write it down again. Not the standard errors, I'm using the expression for the probable errors. It's EX, also carried with the general expression. All right. Z, sorry. So this becomes the general expression if I have to compute the propagation of probable errors, and this is the general expression. Dou f by dou x ex square of it, dou f by dou y ey square of it, plus dou f by dou z ex square of it. That what I have done, instead of the standard errors, I have used the probable errors. And every other expression that we found, multiplication, quotient, power, root, this expressions will be same. Only you have to replace what? Standard errors by probable errors. All right. So the expression propagation will be same. All right. And this is a general expression. Moving on. We have to study about, but you must also note, students, that the modern trend is to use standard errors instead of probable errors. So the modern trend is to use standard errors instead of the probable errors. That's why we studied the propagation of standard errors. Likewise, the propagation of the probable errors are also the same. The expressions are same. The general expression and all the derived expressions, they also come out same. But the modern trend is to use the standard errors or the standard deviation instead of the probable. All right, and the difference between the two is that one is sigma and one is 0.6745 times sigma. All right. So with this, we have completed the propagation of standard errors. Now we'll study about the significant figures in a number. You must be already familiar with, because you have studied the same in your 10+2 classes. But let's revise and learn about significant figures, or significant, I may write it down as significant figures in a number. All right. Significant figures in a number are the digits which have meaning and whose values are definitely known. All right. So the significant figures in a number are the digits which have meaning and whose values are definitely known. That forms the significant figures. Those digits form the significant figures, and we are having some rules how we know how many digits in a certain number are significant. Those digits which have meaning and whose values are definitely known. Number one, the number of significant figures in a decimal number is the number of digits which are certain, and it should be noted that the significant figures are not always equal to the number of decimal places. No, it must be noted that the significant figures are not always equal to the number of decimal places. For example, let me take this example, 135.00516. This is how many significant figures? 1, 2, 3, 4, 5, 6, 7, 8. Another example, let me take 15.0056. This has how many significant figures? 1, 2, 3, 4, 5, and 6. Another one, 0.004150. This has how many significant figures? It has 5 significant figures. 1, 2, 3, 4, and 5. These digits are not significant. Another example, 15.60. This has how many significant figures? 4, 1, 2, 3, and 4. And the last one, 14.3. This has how many significant figures? 3 significant figures. So by this, 1, 2, and 3. By this, you learn that all non-zero digits are significant. All non-zero digits are significant. But the zeros at the beginning are not significant. Zeros at beginning. All right. Zeros at beginning are not significant. Like in this case, it had already 5 significant figures instead of 7. Zeros between the digits are significant. This had 6 zeros between the digits are significant. All right. Zeros at the end are significant because in the same quantity, this had how many? 1, 2, 3, 4, 5. So the zeros at the end are significant. All right. So the significant figures in a number are the digits which have meaning and whose values are definitely known. And it must be noted that the zeros, that all non-zero digits are significant. Zeros at the beginning are not significant. Zeros in between the digits are significant. And the zeros at the end, they too are significant. Or in other words, a zero may or may not be significant, but it depends upon the position with respect to the decimal point and digits, and the zeros which are added just to show the position of the decimal points are not significant. All right, so this was about significant figures. Now let's study about rounding off of numbers. And students, you must note that while reporting your answers in case of a computed quantities, addition, multiplication, whatever, you may not report your answer having more significant numbers than that particular observed quantity which will be having the least significant numbers. For example, let me take an example. You have been given two quantities, 14.3 and 14, let me suppose 15.6720. How many significant figures this number has? 3. This has how many? 1, 2, 3, 4, 5, and 6. All right. Whatever your pocket calculator shows the result, you have to report. Let me suppose this is the case of multiplication. You have to report your answer only to the having 3 significant figures in. All right, so you cannot show it having more than that, because you have to always report your answer in a way that the significant figure in your that observed quantity which is having the least one, it should not be more than that. All right. and the result obtained by calculation cannot be more accurate than the information used. This is the general principle, right? So you may report your answer whatever, only that will be having 3 significant figures. All right, so this was about the significant figures. Or I may also say it like that: when the numbers are added or subtracted, the last significant figure should correspond to the last column full of significant figures. All right, and when numbers are multiplied or divided, the result has significant figures equal to the least number of significant figures of the individual numbers or the information that has been provided. Rounding off of numbers. Rounding off of numbers. Rounding off of numbers is done by dropping one or more digits at the end of the number when there are more digits than those required. All right. So as the measurements are never exact, it is essential to use only the appropriate number of significant figures to express the final results, as already discussed. All right. Now I'll be showing you some simple rules by which we round off the numbers. For a result to be expressed to, let's suppose, n significant figures, we have to express our result or report our result to n number of significant figures. And how we will round off our computed quantities. First one, the nth figure should be retained if n plus 1th figure is less than 5. Rule number 1, nth figure has to be retained if n plus 1th figure is less than 5. 5 number plays important role in case of rounding off of numbers. All right, so we have to report our answer to n number of significant figures, and if nth figure to be retained should be retained if n plus 1th figure is less than 5. For example, 2749.634, we have to round it off to 6 significant figures. 1, 2, 3, 4, 5, and 6. All right, now this drop digit is less than 5. Then I have to retain the nth figure. Then my result will become 2749.63 to 6 significant figures. So the general rule is that if the nth figure should be retained if n plus 1th figure is less than 5. Here my n plus 1th figure was less than 5, then this has to be retained. And I may report my answer as 2749.63 to 6 significant figures. All right, next one. The nth figure should be increased by 1 limit if n plus 1th figure is greater than 5. Nth figure should be increased by 1 limit if n plus 1th figure is greater than 5. All right, let's study this with help of an example. Let's suppose 575836.489. I have to report my answer to 6 significant figures. 1, 2, 3, 4, 5, and 6. All right, so I have to drop this digit, and this digit is what? This is greater than 5. So I may report my answer as 5836.49. to 6 significant figures. All right. So if the nth figure should be increased by, I increased it by one limit, should be increased by one limit if n plus 1th figure is greater than 5. My n plus 1 figure was greater than 5, so I increased my nth figure by one limit. All right. Next one. The nth figure should be rounded off to the nearest even digit if n plus 1th figure is 5. Nth figure has to be rounded off to the nearest even digit if n plus 1th figure is equal to 5. All right. For example, 536.745. If I have to report my answer to 5 significant figures, this will be how much? 536.74. All right, I had to, if my n plus 1th figure was equal to 5, and I have to report the nth figure, I have to round my nth figure to the nearest even digit, but it was even, so my answer is 536.74 reported to 5 significant figures. And my next example, 536.735. I have to report the answer to the same significant figures, and my n plus 1th number is equal to 5. Now I round my nth figure to the nearest even digit, and that is 536.74 will be my answer reported to the 5 significant figures. All right, so this was about some general rules regarding the rounding off of numbers. With this, we conclude today's video lecture. Thank you so much.